Okay, let's get started. So any questions on what we did last time? So how is the homework? How was homework 2?
It was good. I didn't think it was too hard. But I thought it like helped to understand what we went over.
Okay, that's good. That's good. Um, how many people felt it was too long?
I thought it was a pretty good length, not too long.
Okay. Okay, that's good. I think, yeah, the next time you will have, you certainly will have far fewer problems, but the problems will take more time, much more time to think through. So that's, this will vary across the homework. Some of them will be harder. You'll have fewer problems requiring each of them will take a lot more time, and then some which are sort of, we have some concepts we define in the class, and we want to make sure that you have examples to go through and exercise that concept. Can I have more of you turn on your cameras so I have a better idea of what's going on in the class? Great. Keep it going. Okay. I can see more people. I didn't say anything of particular significance yet, so don't worry. I can see more of you on my screen, so I would like more of you to turn on your cameras. Okay. Okay, so we'll okay, very good. So now so let's pick up from where we left off. So we've been going through this example the last couple of lectures. Okay, so so we had this example of infinite strings over 0, 1, and how that could be used to show that the set of real numbers is uncountable, right? And then we started talking about how do you show that the set of natural numbers is uncountable, and we started sketching out a possible approach. And the idea was that just, like here we are constructing a witness that sort of says, I'm not S1, I'm not S2, I'm not S3, and so on. You're trying to do something very similar, which is, if you have an enumeration of these sets, right? Because if you assume that the set of subsets of natural numbers is countably infinite, then you should be able to enumerate them in some order, S1, S2, and so on, okay? And then maybe we can try to construct a witness by basically, picking one element from each set, okay? Or rather, picking one element that's not included in each of these sets, okay? And then we'll be able to say at the end, hey, we have a set S, which is not equal to any of these because it contains at least one element that's not included in each of those sets, okay? So unfortunately, it doesn't really work because there is one corner case which we need to think through carefully, because we are assuming that there exists at least one element that's not included in the set Si, right? But of course, one of the subsets is the set of natural numbers itself, right? And therefore, there is not a single number there that is missing in that set. So you cannot make your S to be different from that set, right? So there is this assumption that every set that is in this list, S1, S2, and so on, is leaving out at least one element, right? That's why you're able to pick one element that's not in that set. But one of the elements in this sequence is, going to be the set of, is going to be the set N itself, because, N itself is a member of the power set of N, right? So one of these elements is going to be the entire set N, and then in that case, you will not be able to find this one element Ni that is not included in that set, okay? So therefore, this approach for construction doesn't quite work, okay? Okay, so is that? Okay, so I'm going to go on and let's think about how we could, make this work, make this proof work. So a little while ago, we went through the exercise of counting the size of power sets, right? And we said, hey, let me find that here. Okay, so I guess I don't have the handwritten text here, but the way we were counting power sets, the size of power sets before is we define a bijection from a set A to binary strings of length A. That is, if A has n elements, right? So this denotes the number of elements in A. So if A has n elements, then we use binary strings of length n in order to represent that set, right? So the way we define this is that the ith bit of a string is set if and only if for some B is subset of A, B includes AI, right? So we said, hey, let A be A1 up to AN. Then we can represent a subset that, say, consists of A1, A2, and A4 as, say, 1, 0. No, I'm sorry. One, 1, 0, 1, 0, 0, right? So let me correct this a little bit. Right, so this time we are numbering the positions from left to right. So A1 is present, so therefore the first bit is set. A2 is present, so the second bit is set. A3 is not present in the set, so we leave that as a 0. A4 is present, So the fourth bit is set and nothing else is present. So we are going to leave everything as a 0, right? So this way there is a one-to-one correspondence between subsets of this set A and binary strings. And then we said, hey, we can count the size of the power set of A by counting the number of possible binary strings of length n, right? So this is what we said, and this is how we count it, right? So why don't we go back to that same old idea and see if we can get, this to work. So we are going to try to, right? So why not apply our idea of using a bijection between subsets and bit strings, right? So we're going to apply the same idea, okay? And in this case, right, because the subsets are going to be countably infinite, right? Because these are subsets of the set of natural numbers. So natural numbers being countably infinite, its subsets are also going to be countably infinite. And so the string lengths will also be infinite. In particular, they'll be countably infinite length, right? So why not take our, represent subsets of n as infinite strings consisting of zeros and ones, okay? And then see what we can do from there. And lo and behold, we get back to the same old problem that we have looked at before. So this is, each of these now is representing a subset of the set of natural numbers. And now we can go ahead and do the exact same calculation as before. And now here is our set S that is going to be different from every set in this enumeration. Okay, so we are able to take our uncountability of n and map it into the problem of uncountability of infinite strings over 0 and 1. Okay, so let's try to think a little bit and try to understand why we failed here, right? And why did we succeed here? Because in some ways, what we are trying to do here is, when we say pick a 1 here, right? When there was a 0, right? What that means, what this 0 indicates is that the first element in the set of natural numbers, right? That element is not included in this subset, but we are going to include that element here, right? Which is very much like saying, hey, let me find a number that's not included in a set and put that into my counterexample set S that I'm constructing, right? So there is, that part is no different. We are basically taking a 0 here and convert, when we are putting a 1 in the counterexample, we are just saying, let me pick that element which is not in that set. And that's going to be my witness to say that this is not that set. So the element is either there or not, okay? So there is no, whether you can find it is a different question, right? So you don't have to be able to find it, right? So somebody tells you the element is there or not. I can ask and it says, do I have that element or not? Because if there's no way to tell if the element is there or not, then we don't even know what the set is, right? So these are all countably infinite sets. So we can ask them to enumerate the set. And we can also ask, whether an element is there or not. Okay, so again, let's not get confused between what is computable versus what is true, right? Things may be true, or false. And that doesn't necessarily mean that you'll be able to verify whether something is true or false in a finite amount of time, right? So what you are, the question that came up here on the chat is, how will we be able to tell if there's an element there or not? Okay, so to verify that an element, is there or is not there might take forever. Okay, so that's what I mean by whether it is computable or not. Let's not worry about that. It's only a question of whether it is true or false. Okay, so we don't need to find it. We don't need to, somebody says, I have a set, I have, right? Again, remember the way that we are constructing this proof is that there is someone who says it is countably infinite and I can list you these sets in some order, right? And then when this person says, I have these sets one by one, then we ask them, well, does it include 0 or not? Okay, so that is the first digit represents whether the number includes 0. The second digit represents whether the set includes 1, 2, 3, 4, and so on, right? So because they are listing these now sets, we can ask them whether some element is in that set or not. Okay, and that's permitted. Okay, so right, let's come back. So this element being 0 simply says that the number 0 is not there in the set, and then we include it in our counterexample set, and that way we are constructing the set. So in a sense, this proof does not seem that different from this construction, where also we are constructing a new set by picking elements that are not included in S1, S2, and so on, right? So why does this proof work, and what is different between this proof and that proof that makes this one work and that one not work? Anybody wants to try? It can be a guess, of course. So Greg.
I think I spotted two differences. The diagonalization proof seems to add the idea of order, and you can not only add an element, but you can also remove an element.
Right, so that is the critical part, that you're able to remove an element, so you no longer have this problem that, hey, I have this set that includes every element, and therefore I cannot give an example of an element that's not in that set, right? Now you can be different from that set by leaving out some element, right? So that's why this proof is different, because you're able to either add or remove elements in order to be different from one of the sets that is being enumerated, right? So for each set, we are different from that set by either adding or removing an element, right? So that ability to remove element is critical, and that's why we are able to get this proof to go through. Okay, very good. So now let's go to the more general theorem, which says that regardless of what A is, right? So far we proved that. So we proved the Cantor's theorem for the special case of where A equals the set of natural numbers. Okay, so with that, we just proved. But suppose we want to prove it in general, okay, for any set, okay, any uncountable set. So then we have to come up with something that's a further generalization. And the way we are going to do this is, we are not going to try to just look at the enumeration of, this power set, okay? Because remember, A may not be enumerable at all, right? Only when A is, the set of natural numbers, then you can even try to enumerate this set of infinite strings. If A itself is not enumerable, then you can't even do this, right? So what we are going to do is, instead of trying to enumerate this set and construct some element that's different from anything in this sequence, we are instead going to directly work with the surjection that we are using for counting purposes, and then say that the surjection has to miss some arrows. Okay, so let's see how this is done. Okay, so once again, let's call the surjection G, right? So we can say that A and power set of A have the same number of elements if we can construct a surjection from A to power set of A, right? Because then the elements of A can cover the elements of the power set of A, which means that power set of A doesn't contain any more elements. So what we need to prove here, and what we have been proving so far about uncountable sets, is that we are such a surjection does not exist, right? So we want to say that if you say that a surjection G exists, I'll show you that it doesn't cover everything. Okay. So the way we are going to do this is this time we are going to ask the person not to just list the elements, but also essentially give you the surjection. Okay, they're going to say, here is the element A, and A maps to this element, right? So we are going to ask them to construct this table. Okay, so let's try to understand this construction, right, using a finite set. Okay, and then we will think about the infinite case. Okay, so we are going to say, let's try a table here. Okay, again, we are asking, someone is claiming that they have a surjection. We are asking them to give us the surjection, right? So let's say, let's take a set with 4 elements, right? 1, 2, 3, 4. And as an example, let's say 1 maps to the set okay, so let's say this is the, right? So now we are going to construct S in this way, right? So we are going to go through each A and ask, is A included in G of A, right? So let's go through, let's take A equal to 1. Is 1 included in G of A? Yes, it is included in G of A, right? So because 1 is there in G of A, right? So if 1 is there in G of A, then it should not be. So S basically says, if A is there in G of A, then I won't include it. If A is not there in G of A, then I'm going to include it, right? So you go through A equal to 1. So G of 1 includes 1. Therefore, we are not going to include 1 in the set. Similarly, G of 2 includes 2. So we are not going to include 2 here. Now, G of 3, on the other hand, does not include 3. So it satisfies this condition, right? So if you put A equal to 3, then 3 is not in G of 3. Okay, so therefore, we are going to include 3 here. Okay, similarly, 4. Okay, similarly, 4 is not in G of 4, right? So it's missing here. So we're going to include that. So the set we construct is 3, 4. Okay, and we are going to claim that nothing can map to 3, 4, Okay, that's obvious in this case because, well, of course, you can see all the elements here, and then you can immediately see that, hey, there is no 3, 4 on the in this finite case. So obviously, the finite case, this is easy to see that it's not there. But let's take a step back and you know, say why it cannot be there, right? So we can now go back and say, right, so we can say let me rewrite this here in a way that I have a little bit more space. Okay, so I'll say that it's not possible for 1 to map to this because, you know, we already know that 1 maps to something that includes 1, right? That's why it's not here in the set S, right? So 1 maps to something that includes 1. That's why 1 is left out of this set, and therefore this cannot match. Okay, same way we can say 2 does not match this. 3 does not match this because originally we said 3 matches something that does not include 3. Okay, whereas here is a set that includes 3. Therefore, 3 cannot map to that. Similarly, we can say 4 cannot map to this because 4 mapped to a set that did not include 4. And here is a set that includes 4. Therefore, 4 cannot be the element that maps to this. Okay. So what we are doing is we are saying we are, again, constructing witnesses, but the witnesses are based on the arrow rather than the element, the set itself, right? So we are not constructing a counterexample to this set, but we are instead constructing a witness to the arrow. If the arrow says, you know, I map an element. If the arrow says I map an element to a set including that element, then I leave that out of my counterexample set. If the arrow says I am mapping an element to a set, I'm sorry, maybe I misspoke. Let me say this again. So if the arrow says I'm mapping an element to a set that includes that element, then I'm leaving that out of my counterexample set. If the arrow says I'm mapping an element to a set that does not include that element, then I'm including that element here. So either way, I'm constructing a counterexample. Okay, so we can also look at it in a. So essentially, what we are doing is that given every set G of A, right, we are constructing, right? So we are given the set G of A for each A, and then we are constructing this set in such a way that for the arrow coming out of A, right? So this is the arrow coming out of A, right? So this is capturing the arrow that's coming out of A. And for that arrow, we are constructing a counterexample or a witness, which basically says that, okay, 1 goes to a set containing 1. And the way I'm going to construct a counterexample is to say, I'm going to construct a set that does not include 1. Okay, so that way I know for sure that the set I'm constructing cannot be mapped at 1. Okay, similarly, the set I'm constructing cannot be mapped at 2, cannot be mapped at 3, and cannot be mapped at 4. Okay, and because we continue this construction, we are able to say that at every A, G of A is different from the set that we have constructed. Okay, so we can also go through this give a sort of a longer proof, okay, which is a little bit more explicit. Okay, once again, the construction is the same, so we don't change anything, right? So this thing says, I'm going to put an element in the set S, right? If I'm going to iterate through all the elements in the set A, right? So I'm going to iterate through all the elements A in the set A, and then I'm going to ask, does A map to a set containing A or not? Okay. If the answer is yes, it maps to an element containing A, to a set containing A, then I omit it from the set S. Okay. If it says I map to an element to a set that does not contain A, then I'm going to put that element in this set. Okay. So now clearly S is a subset of A because I'm going to pick only elements that are in A, right? So this is clearly a subset of A. Therefore, this set A, if there is a surjection, then there must exist some element X that maps to the set S that I have constructed, right? Because S is a subset of A, right? Again, we are talking about power set of A. Therefore, every subset of A must be included, including this one subset that we have constructed. Okay. So now we claim that there exists no X that is going to map to the set that we have constructed. Okay. So there are two cases to consider, right? So let's say, so the proof is going to go by contradiction, right? Which means that I'm going to start by assuming that there exists an element X that maps to S, and then show that that leads to a contradiction, and therefore there cannot be such an X. Okay. So now if X maps to S, then I can ask, hey, is X included in G of X? Okay, so there are two cases. So I'm going to erase there so that I have some space to write. Okay. So there are two cases for X. So case one is X is in G of X, right? And the other case is X is not included in G of X. Okay. So the claim is that X maps to S, which is saying that right? Because it's a map that we are calling G. So if there exists an arrow coming out of X and going to S, then that's the definition of what it means for S to be G of X. Okay, so let's write this down. And then let's ask the question, does X belong to G of X or X does not belong to G of X? Okay, so there are only two cases possible, right? So suppose this is the case, X belongs to G of X, okay? So if X belongs to G of X, then by construction, okay, okay, so I have this. Let me just do the order the same way that my proof has it. Okay, so let's just, right? Okay, so the same cases but this time I put the, does not belong as the first case and belongs as the second case. Okay. So if X does not belong to G of X, okay, then the problem is that by the construction of S, right, if X does not belong to G of X, right, then X would be included in the set S, correct? And S is nothing but G of X. So we have the contradiction that X is in, okay, let's just write it slightly differently. So we have by construction of S, right, X is in X is in S, which means that is X is in G of X, which is a contradiction because we started out with an assumption that we started considering the case that X does not belong to G of X, and then we come back with the assertion that X belongs to G of X, which means that this is not a consistent assumption. So we can do the same thing on this side. X belongs to G of X. Then again, by construction, if X belongs to G of X, then we can say by construction, X will not be included in S, right? So once again, we have a contradiction because we would have left out such an S, such an X from S, okay? And therefore such an X would have been left out of G of X. On the other hand, we are saying that X is in G of X. So once again, we have a contradiction, right? So which means that, it's simply not possible for any X to map to this set S, right? So we have constructed the set as such that there can be no element that can map to this set S, okay? Which means that G is not a surjection, meaning that there are elements in power set of A that are not covered by A, and therefore power set of A has strictly more elements than A. Okay, so this is sort of the more general proof of why power set of any set is larger than the set itself. And what that allows you to do is it tells you that we have already said that the set of real numbers, right, is the cardinality of the set of real numbers is the same as the cardinality of power set of n, right? So we have said that. But then what this proof also shows is that the cardinality of power set of real numbers is greater than the cardinality of R, right? So by going to the power set of R, you can go to and you can construct an even larger infinity. And then if you go for, we can write power set of R, right? So we can keep, creating more power sets, and that way we will end up with, larger and larger notions of infinity, and again, of course, you can do this without end, right? So that's sort of what this Cantor's theorem shows, that there is no, you can keep, there are bigger and bigger infinities. Of course, we have a hard time understanding even the smallest infinity. And so it's not like we are going to do anything with that, with the larger notions of infinity, but it's sort of good to know that, there are many larger and larger infinities out there, okay? So we can, that brings us to the conclusion of this unit, and we will, move on to the next unit about graphs and relations. So your next homework, which will be handed out probably this Friday, okay, we'll cover this unit on relations, especially cardinality, infinite cardinality, and then the graph and relation topic that we are going to cover today and Thursday, okay? And the plan is that once that homework is submitted, then we'll have your midterm, okay? So that's the plan. I'll post the dates by next week. I'll post the exact dates. Let's see. Right. So in before that, we will arrange for some practice with this lockdown browser and taking tests using lockdown browsers. So let's yeah. So you'll have some practice before you take the midterm. So don't worry too much. Any other questions about this unit?
Going back to when we were talking about proving that the power set of n is uncountable, you talked about adding and removing elements, and I was kind of confused on that.
So I was trying to say, what's the difference between this construction, which didn't work, right? And it didn't work because we wanted an element that was not in a set. Okay, so we have all these sets, S1, S2, S3, and so on. And for each of them, we want to pick an element that's not in that set, right? So we pick a arbitrary SI and then say, give me an element that's not in SI so that I can include it in this counterexample set S, right? So that's the crux of the construction here, right? And then I said, well, what if SI is the entire set, right? Well, then obviously there's no element that is not in the set, right? So you cannot construct this counterexample set. Okay, so we are. Right, so so we are not able to construct that set. And the reason why we succeed here is that in the case of such a set, it'll be all ones, right? So for instance, maybe this is the set of natural numbers that contains all ones, right? And the way we are going to construct a set that's different from this set is by removing an element, right? Because we are going to make that, bit position be 0, which means that the second element is not there in this set S that you are constructing, okay? So this is what I meant by when I said you are able to remove elements, right? So you are given this sequence of sets, right? And you're trying to say, hey, I'm constructing a set that's different from each of them. And to make it different, you can either add an element that's not there in that set, right? So we pick an SI. So we have now two possibilities. Okay, pick some K that does not belong to SI, or remove some J that belongs to SI, right? So these are the two actions that we have in constructing the set here. Okay, so that gives us more options, in particular when you have the set of all natural numbers. We can just remove some element from that set, and then now we have a set that's different from the set of all natural numbers. Any other questions? So obviously you should, I want you to be able to understand, this proof, okay? And, anything that relates to natural numbers and uncountability of the power set of natural numbers, I definitely want to make sure that you understand that very well, right? So this proof I know is a little bit harder to wrap your heads around, and that's I teach it with the assumption that some number of people in the class will be able to follow, and some of you may not follow, and that's that's okay, right? So you're going to try your best, but sometimes these concepts are a bit too abstract and too difficult to wrap your heads around. Okay, so that's all right. I mean, that's not to say don't ask questions, right? So ask questions, try to do your best to try to understand what's being said here. But at some time, don't be distressed if things seem a bit too weird. Any other questions?
For this page, I was still kind of confused about why the arrows for 3 and 4 didn't map to S.
No, see, S is just a set, right? So the okay, no, let me. I think I miss. Okay, I didn't read. I didn't. Yeah. Ignore what is said, because I think I understand your question. So we were already told, right? G of 3, okay, does not contain 3, right? This is the information we were given, right? That's why we put 3 in the set S, right? Somebody told us, no, G of 3 does not contain 3, right? So therefore, we know that if we have a set that contains 3, right, then we also know that the arrow from 3 cannot go to the set, right? Because the way we constructed this set is based on the fact that the arrow from 3 goes to a set that does not contain 3, right? So clearly, this set cannot be this set, because this set does not contain 3, this set contains 3. Okay, so that's what we are trying to say. Any other questions? Okay.
I actually have a question.
Yes.
I was just confused about those last two cases where it's like x is not in S equals gx. I was just kind of confused about what those were saying.
Okay. So let's go through this once more.
Okay.
And then we will again it is confusing, and so it's perfectly reasonable to go over this a couple of times. Okay, so let's try this. Okay, let's figure out how to construct. trying to figure out which ones. Yeah, bear with me. I'm trying to figure out how to add a new page and I forgot. So I'm not going to try. Okay, I'll just. Okay. Okay, so let's just try to. Okay, so let's go over this once more, and I will write in the same place, but okay. So we have constructed this set S in this way, right? So we look at the arrows one by one, and then the arrow goes from some element A to G of A, right? And then we ask G of A, do you include A, right? If you include A, then I don't include that A in the set S, right? If it does not include A, then I include that A in S. Okay, so this is the construction of S, and this is the construction of S that we have done, in this finite case to illustrate how S is being constructed, the same construction, right? So the construction is not different. It's something that we roughly understand. Okay, so it's the same construction. Now, all we are saying is that, look, it's not possible for there to be any element X, okay? So what we are saying is that there cannot be any X that maps to the set S that we have constructed, right? So this is the claim that we are making, okay? Which we can say formally as not of there exists an X such that G of X equals S, okay? So no element X maps to this set S that we have constructed. So this is the claim that we want to make, okay? So how are we going to prove this? We are going to prove this by contradiction, okay? So proving by contradiction means we take the negation, okay? And then we show that assuming the negation leads us to a contradiction. So we will assume the negation, which is that there exists an X such that G of X equals S, okay? So this is what we're going to do. Now we ask okay, now let's take this X and let's ask, right? Okay, so we are asking whether is X in the set G of X, right? So there can be only two answers, right? So true or false. So we consider the case X belongs to G of X and then show that there is a contradiction in that case. And then we take the case X does not, I mean, X is in G of X, and then we prove a contradiction in that case too, right? So now let's work through this. So X is not in G of X, okay? So then by construction, okay, such an X, right? Because X is not in G of X, right? So because of that, such an X should have been included in S, right? That's how we have constructed S. So therefore, by construction of S, X belongs to S, right? But then S is nothing but G of X, right? Which that is X belongs to G of X. And then we have a contradiction, right? We start with the assumption that X does not belong to G of X, and then we come up with the conclusion X belongs to G of X, right? And that tells us that this case is not possible, right? Because whenever you have right, so whenever we have P implies not P, right? That's what we have, right? So this is our P, and we starting from P, we are able to prove that not P is true, right? So we are basically showing that P implies not P, and that's possible only if P is false, right? So we have a contradiction, and therefore this case is not possible, and we simply work through the parallel case of X belonging to G of X. And in this case, we'll be able to show that by construction, X, will not be included in S. That is, X will not be included in G of X. And once again, we have a contradiction. We start with the assumption X belongs to G of X, and we end up with X does not belong to G of X. Okay, so again, we have a contradiction, and so we know that, okay, so whatever assumption we started out with is wrong. So this is okay. Now why is this? Okay, so my pen is not working for some reason, but that's okay. So what this means is that the original assumption, I think my iPad maybe crashed. No. Maybe my iPad ran out. Yeah, okay, so. Okay, everything is working now. Okay, so this means that this particular assumption we started out with is false, which means that the original assertion we made that such an element doesn't exist is true, which basically is saying that we have constructed an element S such that nothing maps to this element, which means that we don't have a surjection, right? So there cannot be a surjection because the presence of any surjection leads to a contradiction. Okay, so it's not possible for A to cover power set of A. Okay, that's what we are saying. Okay. Okay, so let's wrap up this unit and go to the next one, which is